Alright, so here we are with the Chapter 5, Section 2 notes on bisectors in triangles. So, we're going to prove and apply properties of perpendicular bisectors of a triangle, and we're going to talk about angle bisectors of a triangle. So, first thing we're going to talk about is concurrent points, and then points of concurrency. Then we've got circumcenter of a triangle, circumscribed, and incenter as well as inscribed. So we will be going through each of those pieces. So in this first one here, since a triangle has three sides, it has three perpendicular bisectors. So what we talked about in our previous lesson was just a perpendicular bisector to a line. But again, because triangles have three sides, we're now going to make three perpendicular bisectors, and what's happening is that they meet at a point. So, when you construct them, you find that they have an intersecting property, meaning right here, and the perpendicular bisector of a side of a triangle does not always pass through the opposite vertex. So, as we're looking at each of these, sometimes people will try to make a line go where they want it to go. For instance, you might try to make it go through this opposite point, okay? But it doesn't always go there. So you do want to just let the line, as you make it, be at 90 degrees, even if it doesn't quite intersect the piece that you think it will. So that's the idea here. Again, perpendicular bisectors to each side of a triangle. So taking a look at what that looks like, it makes what we call a point of concurrency, so that is point P here. It's the point where three or more lines intersect. And then what happens is that makes a circumcenter. What is a circumcenter? It's actually, if I created, and we'll see how good I am at drawing a circle, if I created a circle that touches each of the points here, so that is pretty much the worst circle, this point P is actually at the middle of that circle. So if you hear anything like circumnavigate, circumference, all of these mean around, okay? And so what's happening is the circumcenter is a circle around this center, okay? So that will, of course, lead us to a few things. For instance, notice these blue lines. From the center of a circle out, what is that line called? A radius. And so it turns out that we have all of these radii that are going to be the same length. Alright, we're going to try not to get confused with the fact that the perpendicular bisector, which is what we use to actually make this, is not the radius. Okay, so we want to be very careful that this is not the radius. Versus this blue line here is the radius. So taking a look at what they're telling us in our theorem, the circumcenter of a triangle, so that's P, is equidistant from the vertices of the triangle. So notice P to B, P to A, P to C, all of those are going to be the same. Alright, so another thing about this circumcenter is that sometimes it can be inside, as we just saw, but sometimes, depending on what kind of triangle, for instance an obtuse triangle, your circumcenter can actually be outside. Again, it still is a circle. Notice if I connect each of these vertices of the circle and make it of the triangle and make it into a circle, the circle would be outside, right? Where that would be the center. So that's what happens sometimes, especially with obtuse. And then we also have right triangle, which is very interesting because that is actually on the hypotenuse. And this one is outside, so an obtuse triangle ends up being outside, and then acute triangle is inside of the triangle. An acute triangle has a circumcenter inside. So, just something to look at, and things that might come up are, for instance, which center, because we will have more of these, which center may produce a point outside. Okay, and so it doesn't always go outside, but a circumcenter can. So that one would be one you would list. Alright, this is what I've been mentioning here about this circle. The circumcenter is the center of a circumscribed circle, meaning outside. We will be talking about inscribed circle, which would mean inside, later. But right now we're talking about that circle, again, that just touches each of the endpoints of the triangle and then makes a circle from that. All right. So we're going to find the circumcenter of this triangle here, which means I'm going to plot each of these points, and then I'm going to find all of the perpendicular bisectors and make them intersect. So the first point I have is 0, 0, and then I have 10, 0, and then 0, 6. All right, so this is a right triangle. And so as we just saw, a right triangle is going to end up having a point on the hypotenuse. All right. So I'm going to find the perpendicular bisector of this bottom line here. So what does perpendicular bisector mean? It means bisecting, so in the middle, which would be at 5. And then also perpendicular, which is nice because this one is on a grid paper. So we know that that means that this is the perpendicular bisector of that base of the triangle. All right, then our perpendicular bisector of the next one here, again, it goes up to 6, so halfway is 3. And then if we're making it perpendicular, it is going to follow that line exactly. And of course, because I can't draw perfectly on this, it didn't actually look like it touched the hypotenuse. So, all right. So on that note, if I wanted to create the perpendicular bisector for this side over here, it would in fact go through those two lines. So the interesting part about this is that if I have two perpendicular bisectors, I already know where they meet, and I don't necessarily need the third one to tell me because I already have where they meet, right? So two meeting points, two lines intersecting can only create one intersection point, and so you don't actually need that third line to kind of make it up. So we don't need it. You'll find that, of course, if we were doing this by hand, you would want that third line because most of the time you're off by a tiny bit, and so it's easier to see where the actual point is based on your intersections if you had 3 lines. So due to human error, if you are making this by hand, it's much better to have all 3 of them. So either way, that means that the point of concurrency, or this circumcenter, is at this coordinate, which is halfway between 0 and 10, so 5, and then halfway between 0 and 6, so 3. All right. So the next one, other than around the circle, is a triangle is now inside. Okay, so now we're going to be talking about an in-center of a triangle. So what happens rather than perpendicular bisectors is now we're doing angle bisectors. So again, thinking back to Chapter 5, Section 1, we constructed angle bisectors, or talked about, and then we talked about perpendicular bisectors. So now we're going to take the triangle and, as we just did, do all perpendicular bisectors and do all angle bisectors. Because, of course, a triangle has 3 angles. So let's go ahead and take every one of the angles and bisect it with a line. And if you bisect it, you're going to end up with a point where they all meet. Now that is how to create it, but how to use it is this next piece. So we talked about it in the last one, but the idea is that you're making a circle that is inscribed, meaning it touches each of these sides, doesn't go outside, it touches each of these sides at point Z, Y, X, and makes these radii that are the same. So it makes congruent inner radii. Now again, be very careful, because this one here, as much as it goes to the vertex, it is not a radii. It's just got to be very clear that you are actually going from the center point out and not from a vertex in. So as we look at its description, the incenter of a triangle is equidistant from the sides of the triangle. And remember, we decided that a distance has to be at 90 degrees. And so, again, these are not perpendicular bisectors. So we want to just kind of include that as well. Could it be a perpendicular bisector? Yes, but it doesn't have to be. And so notice that this one does look like it's halfway between, but it's not necessarily going to be. Again, it looks like it, but that doesn't mean it is. All right, so now we've taken all of our angles and bisected them and found where those lines meet. So just a reminder here, the distance between a point and a line, as I just said, is the length of the perpendicular segment from that point to the line. So again, the distance that we're going to talk about as the radius that's equivalent in each of these, if this is the incenter, I need a distance to this piece at 90 degrees. A distance to this one at 90 degrees. Okay, so you want to make sure that you have those in order to get the idea that the incenter has radii meeting it, or congruent radii. Again, here is our inner circle here with its radius in the middle, and then our inner circle here with this center. And of course, because I can't draw very well on this, those do not look like circles. If you want to, you can do this on your paper, but then use a compass. If you put the center of your compass here and then find one of those circles that will allow you to touch each of these lines just barely, then you could make a much better circle than I can right now. All right. The next one says the incenter is the center of the triangle's inscribed circle. Again, what I mentioned was there is a circle inside once you do all the angle bisectors. So a circle inscribed in a polygon intersects each line and it just touches them. Okay, so it doesn't go over necessarily, or basically if you were going to do this on your notes, you'd want to make sure that your pencil goes right on top of this thicker black line that would be there. So we're going to apply a little bit of this. So this is our bisectors in triangles here. So number one, they're telling us that ED, FD, and GD are the perpendicular bisectors. So this word, perpendicular bisector, or set of words, tells us that we are talking about a circumcenter. From the fact that we are talking about circumcenters, they also say that these are the perpendicular bisectors. So we know a lot from that. If ED is something that cuts this in half, then that means this piece and this piece are the same length. It also means this piece and this piece are the same length. And then also this piece and this piece. So again, the idea is that if you know it's perpendicular, we do in fact then know for the bisector part that each of those have been cut in half. So how will that help us? Well, it turns out that, remember, the circumcenter gives us a circle with a center at D, meaning all of these pieces are congruent radii. And this one just isn't shown. And so if this one is 17, for instance, then this one's 17, and this one is 17. And why would that be helpful? Because we have a triangle right here, in fact a right triangle, where I now know that this side length is 8, this angle is 90 degrees, and this hypotenuse is 17. And how will that help us? Because now if we know the Pythagorean theorem, which we do, we can say that our A value is 8, our C value is 17, and then our B value is what we're trying to find. So BD, oh, actually, EB is what, oh, I tried to do that a lot harder than it was. If I just want BD, it's 17. Wow, I was going to try to find the EB, and they want BD. So BD is 17. Haha, yay, okay. Alright. Okay, so then we move on to the next one, and this one says they are angle bisectors. So be careful with that, because angle bisectors means that it's going to be an incenter. And that incenter, of course, gives us some equal radii. And so if we draw this circle inside, P ends up being the middle, and so this is the radii. This could also be the radii, and this could also be a radii. So given that, let's see what we have. They have JP, KP, and HP bisecting all the angles. And we need to find the distance from P, which is the center, to HK, the side down here. Well, if this radii is equal to this radii is equal to that radii, and they're all 3, because they have to be the same length, that means that HK equals 3. So, kind of a lot to look at in each of the pieces, but you just need to remember that anytime that we're looking at bisectors, perpendicular bisectors of a triangle, we're looking at a circumcenter. And anytime that we are looking at angle bisectors, we're looking at an incenter. And both of those will lead to congruent radii. Alright, so hopefully that helps you out, and again, you're going to end up identifying in your homework, is this a circumcenter, is it an incenter, and then kind of match up each of these radii that might be the same.